Cisco iOS provides three sets of tools for frame relay traffic shaping: GTS, FRTS, and class-based. Traditional FRTS uses the command frame relay traffic shaping on the physical interface. It is covered in other presentations. This presentation focuses on class-based shaping over frame relay. Like traditional FRTS, class-based shaping allows us to regulate traffic flow. Shaping buffers traffic when it's at its peak and sends the buffered traffic when the rate is below peak, helping us to avoid egress blocking and ISP policing. Also like traditional FRTS, class-based shaping can create software queues at the interface, subinterface, and PVC level. These queues can then be managed to provide quality of service parameters like bandwidth reservation and priority service. Compared to traditional FRTS, class-based shaping allows us much more control over what traffic gets shaped. We can define classes of traffic based on complex matching criteria and then shape these classes to various rates. We can then combine these shaping policies with marking, policing, and congestion avoidance techniques. Class-based shaping uses the Modular QoS CLI, or MQC. We refer to the MQC as the Swiss Army knife of QoS configuration methods, since it combines many quality of service tools into a common framework. The basic MQC configuration method is to define the traffic of interest in a class map, apply policies to these classes in a policy map, and then apply the policy map to an interface using the service policy input or output command. There are two class map options that are useful only over frame relay. We can match on frames that have the discard eligible bit set in the Q922 header. We can also match on traffic arriving or leaving on a particular PVC. For class-based shaping, our primary shaping tool will be the command shapeAverage. It is with this syntax that we specify the desired committed access rate, committed burst, and excess burst parameters. The shapePeak command shapes at all times to the excess information rate. Few users find this particular command helpful. Adaptive shaping is implemented using the shapeAdapt command. It permits the router to throttle back its sending rate in response to beckon and fecken congestion signals. Traditional FRTS offers additional throttling options. The size of the shaping queue in packets can be controlled by the shapeMaxBuffers command. It ranges from 1 to 4096 packets and defaults to 1000. The fact that class-based shaping policies can be applied at the interface, subinterface, and PVC level add to both the flexibility and the complexity of this method. The level of application affects the number of PVCs that will be affected by the policy. Policies cannot be applied directly to the PVCs. Instead, they must be applied in a map class frame relay, which is then applied to the DELC. In traditional FRTS, we can also apply service policies to the PVCs in a map class, but these policies would not include shaping commands, only queue management policies like bandwidth or priority. To demonstrate class-based shaping, we have set up the lab you see here. A traffic generator is sending two flows of traffic through R1 and across the frame relay links to R2. We will want to apply policies to three different classes of traffic. The first one we call From 6011. This is traffic with source UDP port 6011 and destination UDP port 6016. This traffic varies randomly between 13 kilobits per second and 38 kilobits per second. It averages about 24K. Our second class we call From 6012. It is also destined to UDP port 6016, but the source port is 6012 instead of 6011. This flow has a constant rate of about 40K. Finally, we have the class to 6016. This class is defined as all traffic with destination UDP port 6016. It will include both of the previous flows. As such, this aggregate flow will vary between about 53K and about 78K. It should average about 64K. The clock rate on FRS port S1 has been set to just 64K. Our traffic streams sometimes exceed this bandwidth, so we will implement shaping in an effort to get all the traffic across. We will then implement a bandwidth reservation to make sure none of the traffic from port 6012 gets dropped. Here are the commands that created each of our classes on R1. Note that each match statement references the associated named access list. The access list specifies the source and destination ports for the two classes and just the destination port for the aggregate class, 2616. To verify these flows and their rates, we have created a simple policy called count and applied it inbound to F00. Let's take a look at the results. Here you see the packet counts for each class averaged over the last 30 seconds. Note that class 6011 has been coming in at a rate of 20,000 bits per second. That's our variable flow of traffic. Class from 6012 is coming in at a steady 40,000 bits per second. Here you see the rate has decreased to 18,000 for this class. However, the other class is still a steady 40,000 bits per second. Now we will implement a policy to shape these flows so they do not exceed the 64K access rate between FRS and R2. We will apply this policy at the level of the physical interface to demonstrate the issues. The MQC process starts with class maps, moves to policy maps, then goes to application using the service policy command. However, it is sometimes helpful to analyze the process in the reverse order. Our service policy is applied to interface S00 in the outbound direction. It references a policy called shape S00. Let's take a look at that policy. It references a class called 6016-102. We will look at it in a minute. The shape average command specifies a CIR of 64K, a committed burst value of 8,000 bits, and an excess burst value of 0. iOS will calculate a committed burst value for us, but we needed to specify it here so that we could get past it in the syntax and enter a 0 excess burst value. Remember that if you do not set the excess burst value, iOS will set it equal to the CIR. If we allow this in our lab, then our shaper could send 128K after a long period of time below CIR. However, our CIR is already equal to the far side access rate, and any excess would just be dropped. Now let's take a look at our class map. It matches on our existing class that specifies destination UDP port 6016. However, there is an additional criterion. Matching traffic must be also on DELC 102. Since our policy is applied at the interface level, it would apply to traffic on all DELCs without this match. Unlike shaping with traditional FRTS, class-based shaping allows us to shape just the necessary traffic. Now we will apply this policy to S00. The same policy could also be applied to the sub-interface. We've applied our policy outbound interface 0. Now let's take a look at how this policy is operating. We'll use the show policy enter command. Here you see the 30-second offered rate of 50,000 bits per second for the aggregate. The drop rate is 0 at this particular time. Note also our CIR, committed burst, and our interval of 125 milliseconds. Every 1/8 of a second, the shaper will send 1,000 bytes to the interface in order to achieve our shaped rate. You also see the current queue depth of 6, and the shaping is therefore shown as active. Suppose we wanted to shape traffic at the PVC level rather than at the interface level. Here is an example, again working from the bottom up. When you want to apply parameters to individual PVCs, you must put these parameters in a map class frame relay, like the one you see here. You see that we have used the service policy command within the map class to apply a policy called shape default outbound. Here is the shape default policy. Note that our shape average command has been applied to the class default. This is the only class that can be shaped when the policy is applied directly to a PVC. This does not mean, however, that you lose control of what traffic gets shaped. In this situation, we can control the traffic that gets shaped by controlling which traffic falls into the class default. Class default is the final catch-all class that contains all traffic not previously matched in the policy map. We want to shape only traffic that does match class 26016. We can get this traffic by itself in class default by creating a class that matches everything but this traffic. This is the power of the match not command in the class map syntax. All traffic other than the targeted traffic will match our class not 26016. This will leave only the traffic that does have destination port 6016 in class default. This logic may seem a little tortured, but it is in fact widely used. Now that we have all the traffic destined to port 6016 in class default, we want to segregate it by source port and reserve bandwidth for traffic sourced from port 6012. This is the stream that is sent at the steady rate of 40K. In order to manage the shaping queue, we do a hierarchical policy. The shaping policy is created by the parent policy. In our case, the parent policy is called shape 6016. The child policy is applied to the shaping queue using the service policy command. In our case, it is called reserve, and it guarantees 45K of bandwidth for class from 6012. Note that the service policy command that applies the child policy does not have a direction. The direction is inherited from the parent policy. Also note that the sum of any bandwidth reservations in the child policy cannot exceed the size of the shaping queue. If we wanted to enter our bandwidth reservation as a percentage, it would be a percentage of the parent bandwidth. In the reserve policy, we could have used the command bandwidth %70 and gotten the same result. Now let's see how this policy works. We will remove our old policy from S00 and apply our map class to del C102.